Awesome. Okay, so my name is Kapil. I work as a network capacity planning and forecasting principal at Oracle. What I do day in and day out is I talk to Oracle's tier 1 customers like NVIDIA or Uber. I talk about their inorganic and organic demands and try to manage OCI's backbone network, try to fit in their capacity, fit in their traffic, and make sure we are scaling to making and helping our tier 1 customers manage their data across our cloud. Before Oracle, I was at Meta, and at Amazon, I was doing the same stuff. I was managing the backbone networks, scaling them across both terrestrial as well as subsea globally. A few things that we're going to talk about today. We're going to talk about what a hybrid cloud is. I think pretty much everyone knows about it. And we're going to talk about the challenges that hybrid cloud faces as of today. We're going to talk about the problem of long-term dependencies and the network capacity cycle. We're going to introduce or reintroduce something called as LSTMs. It's a pretty old concept, but we're going to try to embed it into the network capacity planning cycle. And then we're going to talk about a specific use case where we have successfully embedded it, and we have got results, real-world test results based on that, and the future direction on where we are going with some key takeaways to end the talk. Now, this is a basic version of what a hybrid cloud looks like for any customer that's trying to access public clouds like AWS, Oracle, Google Cloud, or Azure. The customer side is generally their on-premise devices or on-premise data center, where they mostly store their legacy applications on some local servers. They also host something called as the customer cage, wherein they are hosting low latency applications, which are pretty much closer to where any of the other clouds connect with them. The Equinix Data Center Cloud Exchange is, let's say, just a data center where Oracle, Azure, or AWS will come in and they'll connect directly to the customer servers. And they do this mostly because the applications that they're serving need ultra low latency or they need a very high bandwidth, and it's the most easiest for them to do so. And from there on, they can access any of the other cloud that they want. So this kind of model is called as the hybrid cloud model. And as you can see, in this one, there are a couple of key advantages to it. There is the flexibility of choice. What that means is you can get the best of both worlds. You can get security as well as control of your own data, especially for sensitive applications. You get ultra low latency because you're hosting it inside the same data center where both the cloud connects in as well as your own applications are hosted, so that you have a direct, secure connectivity between the clouds and your own applications. So that gives you ultra low latency. You also have private connectivity. So a lot of things that we spoke about today was like AWS Direct Connect, OCI's Fast Connect, you have Google's Interconnect. All of these are peer-to-peer networks, which are either 10Gs or 100Gs, in some cases also 400G networks, which are ultra safe and secure because some of them are already running MACsec on it. So based on that, you get private connectivity between your applications which are hosted in your own cloud. Do I need to go somewhere? Sorry about that. Yeah. Okay, good. Thank you. But apart from the advantages, there are some disadvantages or potential disadvantages that come with the cloud, that come with a hybrid cloud model. One is complexity. Managing hybrid environment like this is inherently more complex because then you have to deal with the networking appliances for your on-site. You have to deal with networking which connects to your Equinix data center. You also have to deal with the networking connections between your Equinix data centers application hosts plus your cloud host. So it brings in a lot of complexity for which you need very specific talent in order to manage the entire end-to-end solution. There's also the cost factor. So as you can imagine, you have to not only maintain the cost for your on-premise servers, you also have to pay Equinix so that you can host your application inside a customer cage. And you also have to pay Oracle or any other cloud that you want to access based on their own servers and computes and storage and whatever you want to do in their cloud. So it comes with a trifecta of costs for all of these factors. And then at some point of time, there's also the vendor lock-in case. Depending on the provider that you choose, there's a risk of vendor lock-in, which makes it difficult to move data from, let's say, Azure to AWS or AWS to Oracle or Oracle to GCP. You can always try to mitigate this by carefully planning, but at the same time, you, along with the benefits that you see, the potential disadvantages kind of outweigh that. Now, before I talk about the long-term dependency plan, I'm going to talk briefly about the capacity planning process. When I'm working with all of my customers, there's a certain cyclic process of capacity planning that we always have to go through. We have to start with planning and design, which means talking to our customers and finding out how much capacity they want to send across our Oracle backbone network. That can be either between, let's say, San Jose to Virginia. It can be all the way from Sydney to Japan. But based on what their demands are, we need to plan if our backbone networks are efficient enough to handle that much of traffic coming in from their on-premise devices. And if not, then we have to design or add more capacity so that we can handle that much of traffic for a certain amount of time. And when it comes to designing, it means construction. And by construction, I mean going out to providers and buying that extra capacity from them and installing it. Let's take an example. If a customer, let's say Uber, wants to send 1 terabyte of data from their Sydney data centers through Oracle's backbone network all the way to Virginia. Now we have to lay that trans-Pacific cable or work with providers who can lay the trans-Pacific cable for us from Sydney all the way to San Jose, and then we have to augment our backbone network from San Jose all the way to IID. It comes with a lot of construction, it comes with a lot of time spent, a lot of engineering hours, a lot of tech debt. We have to make sure that once these capacities are installed in our backbone network, we are monitoring them real time. We are making sure that the latency that the customer expects, we have been providing that latency to them at either P999 or P99, depending on the SLA that we have agreed with the customer. And at the same time, there's a factor of maintenance as well. When we deploy a capacity, it falls upon Oracle to also maintain that capacity 99.99% of the time for all of our customers. For that, we always deal with an N+2 redundancy factor, which means that the primary path goes down. There are 2 more paths that can carry the customer traffic, in this example, from Sydney all the way to DC. But at the same time, we need to make sure that the backup paths are maintained and they're up almost all the time. And then the last piece is predictive analysis. This is the last piece where I want to say out of all of this cyclic, 10% of the effort goes towards predictive analysis, where we are kind of predicting based on the customer traffic on how their traffic will grow over the next 1 month, 2 months, or 3 months, or even 6 months. And based on that, we are basically planning 6 months ahead on augmenting our capacity in the backbone. So we are not only maintaining the current capacity, but we are also predicting capacity based on their trends, traffic surges, or if they want to send us new data in the next 6 months, and all of those factors go into predictive analysis. But the most of the effort, the 90% of the effort, is spent from planning all the way to maintenance. Now, as you can see, this is a very, very, I want to say complicated, but a very time-consuming process. So in order to decrease tech debt or manual hours that go into spending all of this time from planning all the way to predictive analysis, we thought of introducing or reintroducing the concept of LSTMs into the capacity planning process. I'm going to talk about LSTMs in the next slide a little bit more, but LSTMs, you can consider LSTMs as a very sophisticated neural network, which is the main advantage of LSTMs is it can remember complex sequential data. So all the way from planning to predictive analysis in regular recurrent neural networks, there's a disadvantage that RNNs cannot remember the sequence of data as it goes or as it flows. When it comes to LSTMs, it can remember the important data that needs to go from planning all the way to predictive analysis and try to reproduce the data according to how the current traffic runs. So it can not only help us to predict the data, it will also adapt to the current circumstances and it will optimize it even better. This is just a quick slide on how we can go from neural networks, which are just an interconnected nodes that take in information, process the information, and send it out to the output nodes, all the way to RNNs. RNNs have a loopback wherein whenever you send information into one of the nodes, it will remember that and it will send the output over to the next one so that it can easily reproduce that data. The problem with RNNs is that when it comes to complex data or where intricate relationships are needed, RNNs fall short of that. That is where we introduce the concept of LSTMs into capacity planning. With LSTMs, there are a lot of factors that go into capacity planning, such as latencies, packet loss, there's network bottlenecks. So LSTMs can remember accurately which data to remember and which ones to discard, and at the same time, adapt on how currently the network is running and try to optimize that process even further. So they do this by two main factors. One is called as the memory cell and the other is called as the gates. So memory cells generally, imagine them as basically conveyor belts, the blue line, the yellow line that you see on the top. These are called as cell states. So memory cells basically remember certain data and they discard certain data, and then they take in the input and send the output out. And the gates help them to remember exactly which data should they process on and which data should they discard. And it's a cyclic and adaptive process, because of which they can keep on optimizing their process even further and keep on optimizing the algorithm even better as more data gets fed into it. The way that we kind of do this right now, one of the main factors is data collection. We send a lot of metrics into our AI model. Most of the data collection that we do right now is we do security lists, network security groups. We input IPs. Those are both private IPs as well as public IPs. We do network traffic, and we also send him latency data. We do this by embedding P999 of 7-day data into our AI model. The AI model is a combination of LSTM, which I spoke about before, and we also introduced some ensemble techniques such as random forest and gradient boosting. All of this will help the AI model formulate the intricate relationships between all of these factors and try to give out the most predictive correct answer based on the current data that gets fed into it. And it's sort of like a continuous process. One of the ways that the model helps us is by dynamically allocating our resources. As you can see, so DRA, or dynamic resource allocation, is a real-time continuous optimization process that acts as an intelligent resource manager. In this process, what it does is, whenever let's say the AI model is completely built in new, we haven't fed in any data, it will initiate the AI model. Second, based on the first input or the first tranche of data that we feed into it, it will make the first set of predictions. Now, these set of predictions are not completely accurate. They may be 40 to 50% accurate. But based on that prediction, it will adjust the resources. Those resources can be computes, those resources can be storage, those resources can be routers, switches. It depends on the output that we wanted to adjust in terms of resource. It does network monitoring as well. Once it has adjusted the resource based on the continuous input of the data, it will keep on monitoring the network. And the last step is model learning, where it will improve based on the number of times we input data into it and the number of times it has to do the predictive analysis. And it will keep making a cyclic loop into making predictions and trying to improve resource adjustment as well as network monitoring. A couple of advantages here is that first one is optimal resource utilization. It prevents both over-provisioning as well as under-provisioning, which in a way kind of either saves us from cost or from bottlenecks. Enhance scalability, allows to quickly adapt to the changing demands. If there's a sudden surge in traffic, it will automatically deploy resources accordingly to manage that sudden surge in traffic. Performance and reliability. By proactively managing all the resources and identifying the potential issues, it minimizes service disruption, and in a way improves the performance and reliability. Next is manual intervention. Because of the nature of predictive analysis in the model, we rarely have to manually put any efforts towards adjusting the resources. We only look at it from a very high level. If there are any bigger events, I want to say, where the AI model is in a very native state and cannot really adjust resources dynamically as we want, only then manual interaction is needed. And the last is cost effectiveness, which kind of goes back into the optimal resource utilization. Before I go into the use case, I want to give a slight overview of how the network behind the scene looks like for any big cloud provider. This is a very generic diagram. This is not specific to Oracle or any other cloud. You have the POP, which is basically a data center. Inside the data center, we have our networking layer, where our backbone routers connect, our internet router connects, our fast connect routers connect, and we have a management layer as well. If you can see backbone routers or the border routers, they have multiple physical routes that go from one location to another. Like I previously said, it goes from Sydney all the way to San Jose, from San Jose all the way to Phoenix, and et cetera, et cetera. We also have the internet layer here, where most of our internet partner comes in and they connect to us. These can be IXs, these can be PNIs, or these can be transit routers, transit exchanges. And we also have Fast Connect. Fast Connect is where our direct customers connect to us. As well, we have partner providers that can help partners or help customers connect to us via Fast Connect routers. And then from the main POP, we also have multiple child sites at each site. So for example, if we take Phoenix, for example, we'll have a main parent site in Phoenix, and then we'll have multiple child sites in Phoenix as well. These will help spray the traffic from our customers into our different compute layers and the networking layers in the background. The way that we do it is we connect the main parent site, which is the POP site, and the child site by metro connections. These are dark fiber connections in the same places. These can be across the street, these can be across 2 points in a city, but these help spray the traffic coming in from all of these customers and all of these partners into our child sites. Now, this is just one child site, but we have multiple child sites at each of our POP locations. Inside the child sites, if you see, we have a similar structure as our parent sites. We have our child sites' own networking algorithms that run into it. We have the compute layer, where all your servers and compute blocks go. And in order to manage the compute block and the networking layer, it's connected by, it's called as the compute fabric network block. It's a very complicated kind of a backbone architecture, but it kind of helps us manage our customers' traffic demands across all the 13 regions that we have presently. Now, the way that we currently are testing our product is that we are running 4 separate scenarios into our AI model. Those 4 scenarios are, we are taking the current state of our network and we ask the AI model to simulate an environment where, 1, we are failing all the routers one by one by taking the 7-day data, with 30% increase in LSP demand between all the regions. We are also, the second scenario is we are failing all SRLGs one by one with increase in 30% demand. And the last two are just failing all routers one by one or all SRLGs one by one. And as you can see, these are the latest results that we see. The one on the left, as you see, is a scenario which I have chosen, which is the second from last scenario, where we are failing each of the routers one by one, and we are asking the AI model to kind of simulate how the traffic will perform if one of those routers go down. And it will automatically generates a list of source and destination regions for us, which get affected if one of those routers are basically if one of those routers go down, either because of any of the reasons. So if you see, the first one is, let's say one of our Toronto routers, let's say, goes down, it's going to affect the Toronto to Montreal region. And how does that affect it? Is if you go down here, you can see the steady state path right now is directly a connection between Montreal and Toronto. But let's say if the router goes down, it will take the backup path, which is going from Montreal all the way to LaGuardia and coming up back to Toronto. So it induces a certain amount of latency. So let's say if it's 4.5 milliseconds of latency as a direct point-to-point connections, because it's taking a backup route, the AI model shows us that it's going to increase the latency to 9 seconds. Now, this latency that you see is not real-time latency. It's very difficult to integrate latency into the model that we have right now. That's why what we have done is we have introduced as crow flies latency, or basically as light travels through vacuum. So this is not true latency, but it kind of gives us an idea of, okay, if your router is going down, you're going to have to take the backup route and your path latency is going to increase. That helps us make a determination of, okay, we need to either increment our capacity or augment more backup routes, so that even if our main primary router goes down, we have another router which can take the traffic for our customers between those two locations and maintain the 4.5 milliseconds of latency. If not, we can take the backup route and we can inform our customers that, okay, if the first direct path goes down, then you can expect a 100% jump in latency until we restore the route. This is another example where if we fail our routers in Jeddah, for example, the Jeddah to Abu Dhabi route gets affected. So in this case, the steady state was an indirect path between Jeddah and Abu Dhabi, where we are going through Dubai. But if the Jeddah router goes down, for example, our traffic will basically go all the way over to Paris, which is Marseille, and then going down to Abu Dhabi, because that's the physical backup route that we have. That will introduce a latency of around 285%. Now, this is again giving us an idea that, okay, your capacity between Jeddah and Dubai or Dubai to Abu Dhabi might be less, and you need to increment that more so that the backup route doesn't get introduced. That is how currently we are using the native AI model. We are also trying to test it with more compute instances, storage instances, so that it can automatically scale that for us. But at the moment, we have a successful model running in our backbone network where it's kind of predicting what the path will be and what the latency will be as well. And it's giving us corrective actions on what we need to do in order to not fail over to the backup path, because it's not going to be SLA compliant with our customers. Now, what this has done for us is basically that model itself, just by testing it on our backbone routers, has lessened our cost by 18%. When I say $10 million, when it comes to networking, it's not a very big amount. It sounds very big, but $10 million is something that we could easily spend quarter over quarter to augment our capacity across the globe. So because it's giving us exactly which router or which path to tackle or which path to augment in case a certain route goes down, we have already started augmenting our paths so that our customers don't have to fail over in the backup routes. And that's how it's reducing the cost for us by 18%. It's giving us uninterrupted performance. we are measuring specific performances like latency and throughput because of the model, and because of the predictive analysis that the model is giving us, we are able to maintain our backup routes or our augmented routes within acceptable range. We are able to we are trying to teach the model to tackle complex problems. For example, it's right now working on predictive capacity analysis. Let's say if tomorrow Uber comes in over a Thanksgiving weekend and says that we are going to expect a lot of traffic because a lot of customers are going to order Uber Eats over Uber Eats. So that's going to increase a lot of traffic for them, and maybe they are hosting some applications in Oracle Cloud or somewhere else for which they have to use the Oracle network. Now that will basically increase the complexity for our model, where the traffic surge may be by 30%, by 40% or 50%, we don't know. So we are trying to teach the model on how to tackle that complexity on the basis of whatever factors that get inputted into it. It should try to do that corrective predictive analysis and try to give us the right data on exactly what path or which particular element in the network should we augment. We are working on trust to transparency. What this basically means that the whole AI model, as you see, is kind of a black box. We really don't know the decision-making process behind the AI models and why does it predict in a certain way. So we are investing in something called as XAI or explainable AI, where it can teach us exactly the thought process behind each of these models and what makes it take certain decisions. We are also trying to continuously adapt by giving it as much data as possible over a certain period of time. Right now, we are feeding it 7 days worth of data of P999 data biometrics, but we are also trying to give it P999 1 day, 2 day, or 3 day data, depending on how complex and how easily predictable the model works and how accurately it gives us an answer. So a couple of conclusions. One is hybrid cloud. It does provide flexibility and scalability, as we saw earlier, and a lot of customers are still adapting or onboarding hybrid cloud. There is a certain challenge when it comes to network traffic, and it can be predictable or it can be unpredictable. But we are doing everything possible from both a manual perspective as well as an AI perspective to tackle that unpredictable network traffic challenge. We have tried to embed a model using LSTM, sorry about the mistake there, wherein we are kind of coming up with a smart solution for our own internal use, where we can try and improve our network's efficiency and help our customers maintaining SLA ranges or SLAs in an acceptable range. And at the end, we also saw some real-world test results where it's kind of making sense to us that if we try and onboard this model into a more larger process, it's going to give us more cost savings, and it's going to help us increase the performance even more. So it's a work in progress right now. We have used it in our backbone networks for now, but we are also working on increasing the adaptability into computes, into storage, into databases, and see how the model works when it comes to all of these factors on the cloud. And as always, our mission is to help people see data in new ways, discover insights, and unlock endless potentials. And I think I might need help. But anyways, I was done. That was the last slide, by the way. Thank you.